And welcome to our webinar, AC Interference, Threat Assessment, Standards, and Compliance. It's the third session of our AC Interference series. I'm Anna Wilson, Corporate Marketing Manager at American Innovations. If you need to catch up, you can access all the other ACI sessions on our YouTube channel or check out our website, aiworldwide.com, in the resources section. I am here with your panelists today, Andy Florence, American Innovations Director of Pipeline Integrity Management Services, and Jordan Grudy, Director of Technical Services for Bass Engineering. If you have any questions, just go ahead and submit them and we will answer them at the end. Don't worry if we don't get to your question, we will reply to you by email. Without further ado, I'm going to send you over to Andy and enjoy the session.
Anna, thank you so much, and everybody who's taken an hour out of their busy schedule to share with us part 3 of a 4-part webinar series. I want to thank you as well. It's a great time to be in the oil and gas industry, really good time to be in the pipeline industry, a lot of pipe and metal going into the ground. So I think hopefully this webinar series will be a relevant topic for you as you begin to work closer and closer in an urbanized area in closer proximity to power lines. As Anna said, my name is Andy Florence. I'm the Director of Pipeline Integrity Management Services for American Innovations. I've been doing this job for about 11 years now and have really enjoyed every moment of it. My colleague, Jordan Grudy, is based out of Longview, Texas. He is the Director of Technical Services out of Bass Engineering. For those of you who don't know, American Innovations and Bass Engineering are two sides of the same coin. We have a common executive management team, a common board of directors, and common owners. However, we're two very distinct entities. We like to think of ourselves on the integrity side as the inside dogs. We're the computer jockeys. We do the data analytics and the analysis, processing large volumes of data to create information, which then drives the work for the outside dogs, which is Jordan and his group out in Longview, who drive the Ram 1500 pickup trucks and get their boots dirty and actually get out and touch the pipeline. They're the guys who get out in the field, collect the information or the data points that we need, feed it back to us, we turn it into information, and then feed it back to the guys out in the field and tell them where to go. So they don't have to spend any more time out in the 100-degree heat than they have to. So with that, let's go ahead and get started. Before we do get started, if you have any questions, you should see a button on your webinar screen there to ask a question. We'll be collecting questions and holding them till the end, and we'll answer those. But feel free to type in your questions and send them to us, and we'll try to address them at the end of the webinar. As I mentioned before, this is part 3 of a 4-part series on AC interference. Our first session was approximately a month ago, where we actually defined AC interference. We told you what it was and told you what to look for when you're out in the field. What are the characteristics of AC interference when you've got when you're out in the right of way and you're looking at your pipeline or you're looking in the ditch? How do you know if you have AC interference? What are you looking for out there? We characterized AC interference as a multi-headed monster, something that you're never actually going to be able to kill, but you can certainly tame this monster. And in order to tame that monster, that was kind of the topic of our second session, mitigation options. Once you understand what AC interference is, the different types of AC interference, we gave you some tools to put into your toolbox to get out there and to suppress or to control this monster and keep it on a short leash. So you had your mitigation options. Today's topic is the third session. Today we're going to be talking about AC threat assessment, ACI threat assessment. The objective is to help you understand, to give you a primer on all the elements that you need to implement an effective AC mitigation program. In other words, how do you manage this monster over time? You have limited resources, limited time to address a problem each year. So where do you take those limited resources, those valuable resources, and efficiently allocate them to where this multi-headed monster is going to be appearing? And then finally, a week after, or a couple of weeks after this session, we're going to talk about monitoring and exactly how do you, as I said, you'll never be able to kill this monster. You'll be able to tame it, so it's still alive and still happening out there. So you need to monitor, continuously monitor this phenomenon out on your pipeline. So we'll talk about monitoring and offer you some tools to help you effectively keep an eye on this monster out on the right of way out there. So let's get started. A quick review of some of the previous two topics. We'll start with the definition of AC interference. For those of you who don't know, INGA, which stands for the Interstate Natural Gas Association of America, commissioned a report about 3 years ago to succinctly define or provide some guidance to the industry on what AC interference is. You got to feel sorry for the guys who were part of this project, because if you've ever read the documentation or perused through the documentation on AC interference, there's a lot of documentation out there. Some of the earliest documentation I've read goes back to the 80s. So these guys were tasked with reading all of that documentation and bringing it down into a succinct one report that gave you some guidance and definition of AC interference, and also gave you some very clear criteria for evaluating whether or not you have AC interference on your pipeline out there. They did a really good job. If you haven't read this report, I suggest you go out and download it. We'll provide the link to you a little bit later. But it's about 122 pages of surprisingly easy read, and it gives you a good basic understanding of AC interference. The definition you see on your screen here comes directly from the INGA report. In layman's terms, it's basically this. If you've got a pipeline laid and working in close proximity to a power line, two things can happen. One, you can have damage to your pipeline, or you can introduce a safety hazard to your personnel along the pipeline. Very simple, basic definition. If you're working close to, if you're out on the right of way, you look up and you see a power line, first thing that comes to mind ought to be, I might have the potential for AC interference on my pipe. Session one, and earlier defined specifically 3 types of AC interference. Capacitive AC interference. This is the effect of the isolated pipelines sitting on during construction, sitting on a wooden skid, and the metal in the pipeline becomes a conductor, and you've got charge voltage being generated on the pipeline. Your construction guys, your welders, they know how to handle that. You take a piece of rebar, drive it into the ground, take your jumper cables, touch it to the connect it to the rebar to the pipeline, and that bleeds the energy off of the pipe, and it's safe to go about doing your construction and your welding and things that you do during the commissioning of the pipe or construction of the pipe. The second type of AC interference was resistive coupling or resistive interference. It's an intermediate threat. It occurs when there's a fault on the power line. There's an abnormal condition or unexpected condition, fault condition on the power line, releasing the energy into the environment. Typically, it'll happen along you have a 60 hertz fault event or a lightning event. That energy travels along the power line down to the guy wires, down into the ground, and then can, effectively damage your pipeline. If you also happen to be touching the above ground pertinences or the pipeline at that time, then of course you get the hazard of the step potential, touch potential, and the threat of that energy traversing through your body and causing injury, even death. So resistive coupling, resistive and capacitive. And then the third type of AC interference was inductive. I'm going to hold off on this one a little bit because we're going to talk about this one in great detail, inductive coupling. We're going to use this as an example for walking through our risk assessment out there. So session one was 3 types of, give you a definition of AC interference and identified 3 types of AC interference. And then happily, about a year ago, late last year, NACE came out with a standard, SP 21424, which gave our guys out in the field some guidance on some standard practices and some guidance on how to implement an effective AC monitoring program out there. And I say happily because it came out and corroborated a solution that we, American Innovations and Bass Engineering, have been promoting for a couple of years prior to the release of the standard of the SP, recommended prior to standard practice. We're really happy to see this come out in a formal recommendation from an organization like NACE. In effect, what NACE is telling you that you need to do is 4 steps, 4 high-level steps. First, you need to do an analysis, which is the equivalent of a risk assessment of all of your assets. This is to help you understand where along your pipeline you have the potential for AC interference, where all the right conditions and the confluence of events and circumstances that come together to introduce AC interference along your pipeline. Once you understand where the AC interference is, then you can develop a mitigation strategy. And again, in session 2, we covered not only the different types of mitigation that you can implement, but also some strategies for modeling and also engineer field design. So there's some very sophisticated modeling tools out there that help you understand the AC interference, as well as some practical experience. When you're out in the field with your engineers, you can look at, make an assessment, do some mitigation while you're out there. As I mentioned earlier, this AC interference is a monster that you will never slay. The best you can do is tame it. So you need to develop a monitoring strategy to continuously monitor this phenomenon. And then finally, in step 4, at a high level, you need to do the actual monitoring. So NACE has given you the actual 4 steps to implement a very effective AC monitoring strategy or AC monitoring program. And coincidentally, our presentation this presentation today is going to speak directly to that first step, analysis and risk assessment. So with that, let's take a break and let's do a poll real quick. And guys, give me a second here as I navigate to the poll. And I'm going to ask you, does your company presently have a formal risk-based AC interference monitoring program? And as the polls are responding, people are responding, answers are coming in, let's ask the question, if we're going to do a risk-based inspection, let's ask this question: what is risk? Risk, if you ask my 17-year-old son, he'll tell you it's the likelihood of him not getting his allowance for the year. And I'll tell him his mitigation activities is if you come in within your curfew, you get your allowance out there. The point of that little story there is that if you ask different people, you'll get a different answer what the definition of risk is. They generally understand that it's some kind of a loss or something bad that's happening, but risk is you get a different answer out there. So it looks like we've got 60% or 62% of our folks have actually responded to our survey. 57%, you guys are still replying. 58% now. Looks like it's about a 60-40 split. About 60% of you say no, I don't have a risk-based monitoring program for AC interference, and 40% of you, approximately 40% of you, say yes, we have a formal process in place. So for those of you who do have a formal program, hopefully what we show you today aligns with what your program does. If it doesn't, then hopefully we're giving you some new information to consider as part of your program. For those of you who don't have an AC monitoring program, I hope you find this enlightening and a great primer for starting your program out there. All right, let me close this here real quick, and let's move on to the next slide. So again, I said if you ask 10 different people what risk is, you'll probably get 10 different answers. And fortunately, your federal government, your tax dollars at work, the federal government has given you a definition of risk. So risk is defined as a measure of potential loss in terms of both the likelihood of an event and the magnitude of the consequence of the event. And I intentionally underscored and bold-faced the term measure here, because if you're going to measure something, that means that you need to quantify it. You need to put a number to it. You got to find a way to put a number to circumstances or events or something so that you can measure it. So how do you measure risk? Well, the federal government also, by reference, will tell you that risk is defined as the likelihood of failure times the consequence of failure. So each of those numbers, each of those variables, likelihood of failure and consequence failures, represents a number which represents the riskiness of some confluence of events that come together to create a loss. The consequence side of the equation, typically there's nothing you can do about that. It is what it is. If you've got a pipeline that runs through a densely populated area, or it runs through next to a hospital or a school, it is what it is. You really can't affect that change on that side of the equation. You have to be cognizant of it, you have to be aware of it, and you need to include it in the overall risk as to help prioritizing your work. But there's not a lot you can control on the consequence side of the equation. On the likelihood side of the equation, likelihood of failure, there are a number of risk factors that you can control to mitigate and to reduce the likelihood of occurrence. And we're going to talk about that in a little bit greater. And so the focus of the remaining of our presentation is going to be on the likelihood of failure side. It's not to minimize that you shouldn't be considering consequence of failure. It's just that the things that you can typically control are on the likelihood. So that's what we're going to talk about here in the next few slides. You know what? I still got my poll open. Let me do this here. I forgot to close it. Sorry. Hope that did not overlay some of the screen slides that I were presenting here. So let's talk about risk. If it's a nebulous, intangible thing, what is it that you have to do to start breaking this problem down? So it's, how do you quantify something as complex as an intangible as AC interference? And the answer is, well, you take some commonly used industry practices and concepts, and you decompose this phenomenon down into its basic elements. And once you understand the basic elements, you can start implementing a strategy to mitigate or taming this beast. So so to do that, we developed a framework that allows us to basically categorize all the different components of our threat. At the highest level, we think of a threat. And we define the threat as an indication of something that is impending. In ACI, for example, step or touch potential, accelerated corrosion, and instrumentation damage. Those are all threats that you have to consider when you're doing an AC interference study. If you break it down even further, then you have a mechanism. You need to understand what are the processes and the series of events that can occur which bring the threat to reality. So a mechanism is a natural or established process by which something takes place or is brought about. For ACI, we consider inductive, capacitive, and resistive. Those are the three mechanisms for AC interference which bring the threat to reality. Mechanisms then can be broken down into factors, risk factors, what we call threat or risk factors. A factor is something that actively contributes to the production of a result. And examples in AC interference, ACI would include AC current density, co-location density, and soil resistivity. So those are just a subset of several different risk factors that you would consider when you're doing your threat assessment for ACI. And then finally, again, on the consequence side of the equation, you need to consider your receptors. It's a bit of a cold calculation and a cold term, but at the end of the day, you need to understand it. So a receptor is an object that's impacted by an abnormal event or failure. So if that threat comes to reality, who or what on the back is going to be on the receiving end of that event. And so for ACI, we consider assets, your pipelines and your instrumentations and your things like that, as well as people are considered receptors. So now I have a framework which I can start decomposing this complex monster, this complex problem down and breaking it down into easier to understand in a logical set of factors or however you want, logical set of considerations for helping understand AC threat assessment. So the next few slides, we're going to take our threat framework and we're going to apply it to inductive coupling. Remember now, inductive coupling is one of the mechanisms for introducing a threat to our pipeline. And if you remember from session 1, we called out, or we described inductive coupling as the effect of the electromagnetic field that's being generated from the power line, energizing the air and the ground between the pipeline, acting like a transformer, a step-down transformer, and putting energy onto the pipeline. Even if it's buried, there's still the transfer of energy from the EMF energizing your pipeline. Some of the newer technologies, so that energy, once it gets onto the pipeline, is looking for a place to discharge off of the pipeline and get down into the ground. And so with our newer coating types, our newer technologies around external corrosion, FBE, for example, fusion bonded epoxies, well-coated pipes, very few holidays, high resistivity on the coating, so there's very little opportunity for the charge to get off or discharge from the pipe. If it does find an anomaly or a holiday in your coating, then that's where the charge is going to try to discharge, and that's going to create a accelerated corrosion at that point. So while we tried to mitigate external corrosion with better coatings, we exasperated another problem with AC interference. We just need to be aware of that. So let's take our framework and apply it to inductive coupling. We have the threat, as we mentioned before, is accelerated corrosion on my pipeline. My mechanism is inductive coupling. My risk factors, I'll hold that thought. We're going to do a deep dive on some of these risk factors for AC, for inductive coupling. We're going to do a really deep dive on these factors and explain to you what you need to consider. And then finally, the receptor in this case is, we think of it as the pipeline receiving accelerated corrosion. So I've got my framework. I now know what I'm going to address. Let's start looking at, well, before we do that, let's go back and do a poll real quick. Let me go back and bring out the poll. I'm going to ask, have you ever experienced AC corrosion on your pipeline? How many of you out there have actually seen accelerated corrosion due to inductive coupling on your pipeline? There, the results are coming in. Looks like so about an even split here. About 50% of you say yes, you experienced it. 50% of you are saying no, you've not seen it on the pipeline before. So interesting split. About half of you have seen it. You know what to look for when you're out on the right of way. The other half of you are saying no. And so appreciate your time there. Very interesting. So let's close out our poll, get back to our presentation. And let's talk, oops, sorry, wrong button there. So let's talk about risk factors. I can actually, for this example, we're going to be grouping all of the risk factors for inductive coupling into 4 buckets. And our first bucket here is we think of it as the geospatial relationship of the power line to the pipeline. And the 4 factors that we're going to look at is the separation distance, the co-location length, the pipe, how much of that metal is in the shared, is exposed to the EMF field, what is a crossing angle of the pipe to the power line, and then what we call an inflection angle or the bend in the pipe. So those are going to be risk factors that we consider. We'll talk about those in greater detail a little bit later. And then you need to talk, and then the other bucket is the power line operations. If you have your AC current, your HVAC current, and you can get that information for the power line that you're co-located with, that's the data that you probably want to use in your threat assessment. For those of you who have ever tried to call a power company and ask them to give you that data, once the power representative stops laughing at you, he's going to ask you for a check, and he's going to ask you to come back in 6 months. So you're not going to be able to get that data easily unless you're a large distribution company who happens to be distributing both electricity and gas or pipelines. If you're lucky enough to be able to get the HVAC current data, you're welcome to use that. I'd suggest you use that data. You could use, however, HVAC voltage as a proxy, and I say that is because there are some third-party data sets available out there that you can purchase relatively cheap that show you the center lines of the electrical transmission power lines, and they give you the voltage ratings on those power lines out there. So you need to use one or the other, voltage or current, but don't use both because then you're double dipping in your risk modeling. But pick one and use one or the other. Once you have your power line operations, the next bucket that you want to consider are your environmental conditions. If you've ever talked to a corrosion guy, the outside dogs and like Jordan and those guys, you start talking about CP and corrosion and things like that, first thing they're going to ask you is soil resistivity. Just like external corrosion management, soil resistivity plays an important risk factor in considering AC current density or AC interference, excuse me. And then finally, the design of the pipe is going to be a critical risk factor. So several critical risk factors that you need to consider in your threat assessment. Most importantly, your coating resistance, and we'll talk about how we create a composite risk factor using the coating condition, the coating age, and the coating type. And then finally, the pipe diameter can actually play a role in your risk assessment as well, or your threat assessment as well. So this is not a comprehensive list of everything that you might want to consider for your AC interference, but we're going to walk through these risk factors, show you how we would put them into a risk-based inspection or risk-based threat assessment, and then you can take those same concepts. You'll see a pattern developing over time. Take those same concepts and apply them to other data that you might want to bring into your threat assessment. So let's walk through a real live example. When I first started putting these presentations together, I saw this picture and I quickly knew that I had all the right ingredients in one image to explain inductive coupling and AC interference out there. The first thing that I noticed when I saw this picture were these steel lattice towers out here, considerably large structures. So it's a pretty safe bet to say that that power line is carrying is built to carry a pretty big load. So we're going to assume, just for this example, that this is a 500 kV HVAC power line. Pretty powerful energy structure, source of energy out there. This is also, for the sake of this argument, let's assume this is a transmission pipeline. Main line is carrying an HVL. It's a Y-grade NGL pipeline, so it's an HVL product. We've got it coming into a yard here, the transmission coming into the main line coming into the yard. Looks like there might be some traps and things in here, some valves, some above ground appurtenances inside of the yard, and then the suction line coming into our pump station. Our pump station, we actually see 3 pumps here. We have our suction header lines, our discharge header lines coming back out to our discharge line and then back out onto the main line, pushing the product on down the line. So this is going to be the scenario, or we're going to walk through the potential for induced AC interference, inductive coupling, sorry, on these assets in this particular image. For those in the corrosion world, I know the corrosion world and the integrity world, the inside dogs and the outside dogs, they talk different languages. We look at our assets differently. For the sake of this example, we're going to use the terms that the integrity management group tends to use. I know that you guys out in the corrosion group, your corrosion techs, you tend to refer to your pipelines as right-of-ways and mileposts and things like that. Your integrity group and your GIS group will refer to your pipelines in segments, or now pipeline segments or routes. So just to level set everybody, in this example, we're going to use the term the integrity managers use, and we're going to say the first part of our little segment here is the red segment. Our main line is the red segment. Everything inside of the yard we're going to call the blue segments. everything from the yard into the pumping facility. We're going to call them the orange segments, the piping in the facility. And then back out on the main line, again, we're going to call that the green segment. So not unusual for your integrity group to break these, to break your pipelines up into segments that help them to manage the data a little bit easier. Okay. So let's get started. First thing that we're going to do is and when I say we're going to say, just understand that we actually did this for a customer. This was the approach that we took, and this is how we implemented our AC interference threat assessment for them. So our GIS team got the center lines for our pipeline from our customer, as well as the center lines for the power transmission from third-party data sets. And then we merged those data sets together. And the first thing that we did is what we called fixed segmentation. We divided each of the pipeline segments up into smaller 25-foot segments. So you can see here, again, this is not the scale. This is not our actual customer. This is all, all obfuscated, but it does demonstrate the principles that we did for our actual threat assessments that we do for our customers. So each segment, a pipe, is divided into 25-foot, what we call analysis segments, and then we're going to apply our risk threat framework to each of those analysis segments to come up with a risk score for each of those analysis segments. How risky is that little 25-foot segment of pipe using our risk factors and our threat assessment framework? Okay. So those are the terminologies we'll be using for the rest of the slides here, the remaining few slides. Again, each analysis segment is assessed for ACI based on the risk factors that we discussed, we defined earlier. So let's start walking through our scenario here and applying our threat assessment to our facility here. You see the bucket here. These are geospatial relationship. We're going to talk about separation distance. Every little risk factor is going to be given a little conversion table down here. So this first column right here represents the actual value of that risk factor for that analysis segment, the little 25-foot analysis segment. And then to make it easy to talk to, we're given a high, medium, low risk score just to make it easy to talk to. But based off of the value, the instance value of that particular risk factor, we're going to give it a risk score on a scale of 1 to 5 or a scale of 1 to 6. There's a reason for the 1 to 5 and 1 to 6 based off of the supporting documentation that we read. But you're going to get a risk score based off of the value of that risk factor. And so 0 to 5, the higher the risk score, the riskier the asset. So no surprise, in the case of a separation distance, right, the distance between a point on the pipeline at a right angle with the power line, the closer the pipe is to the power line, the higher the risk. All right, so let's take a look at our little scenario here. And we're just going to take one analysis segment, the orange analysis segment, randomly chosen right there in the middle. So starting right in the middle of that 25-foot analysis segment, we're going to measure the distance from the middle of that analysis segment to the right angle of the power line, that 90-degree angle. And that comes out to be 450 feet. So you're saying, Andy, well, do I got to go out into the field and measure the distance and do this for every 25 feet along my pipeline? You do not. If you have a good GIS team, they can do this for you. There are Esri tools or GIS tools available to do this for you and to do it on the computer. So you come back with and do this through automation out there. If you don't have a GIS team, give me a call. I've got some really smart GIS folks on staff. We'd love to help you. But in this example, you can see here at this analysis segment right here, from here to the power line, it's 450 feet. So I go to my little conversion table down here, and I see that from 101 feet to 500 feet, that's a medium risk. So I'm going to give that risk factor for that analysis segment a risk score of 3. Mm-hmm. And then I'm going to do the same thing for a blue segment, Again, from the middle of that analysis segment to a right angle at the power line, I got 375 feet. Our GIS team measured that based off of their GIS tools. Excuse me. And so again, that analysis segment is going to be looking at my little conversion chart here, 101 feet to 500 feet. It's a medium risk. It's going to get a risk score for that risk factor of 3. A little bit further away from the pipe, 1,200 feet, that first red analysis segment, 1,200 feet. Go down, look at my conversion chart. I see 1,001 feet to 2,500 feet. No surprise, the further away the pipe is from the power line, the lower the risk. It's very low risk, and we're going to give a score of 1. Let's take a moment and understand what the less than 2,500 feet is and no risk. So the guidance that we've seen in some of the documentation tells you to buffer around your pipeline on either side of the power line, buffer on the power line, either side of the power line up to 2,500 feet. So obviously you've got pipeline that's not within 2,500 feet of the power line. So we're only going to consider all of your assets, all of your pipeline and your above ground appurtenances that are within 2,500 feet of the center of the power line on either side. So you've got basically a half mile on one side, half mile on the other side. A mile is really the scope of the study for which we will be conducting the threat assessment. Okay. Let's go back and look at the next slide. So now I've got then there's 25-foot little green segment. There is 25 feet away from the power line. So looking at my conversion chart here, less than 100 feet, that's a high risk. That particular analysis segment is going to be given a risk score of 5. That same pattern that we just did for separation distance, we're going to start applying that to all of our risk factors. So now let's look at co-location length. Co-location length is defined as the continuous length of pipe that is within 2,500 feet buffer of a power line. The more pipe that's co-located with the power line, the higher the risk. It just makes more sense, right? You got more metal, you got more conductor in the ground, so you got a higher risk of getting energy induced onto your pipeline out there. So let's talk about how we would look at co-location length for my scenario here. And again, what we're going to take a little bit different approach on the analysis segment. We're going to look, because we're talking about contiguous lengths of pipe, we're going to look at the entire length of the pipeline segment and then look at that as a risk factor and then apply that to the individual analysis segments. So for example, we see that our red segment coming into the yard here, our little red segment is 1,800 feet in length. It's within the 2,500 foot buffer. So I go look at my little conversion table down here and I see that 4,999 feet to 1,000 feet of co-located pipe is a medium risk. And so we're going to give that a risk score of 3. Every red analysis segment, we're going to give that a score of 3. 200 feet within my 200 feet of contiguous pipe within my yard. Looking at my conversion table here, I can see that it's a lot less metal being exposed to the magnetic field. So I'm going to give that a risk score of low. Sorry, it's going to be considered low risk. It's going to be given a risk score of 2. Right? So every blue analysis segment in our analysis will be given a score of a low risk score of 2. Same thing, 900 feet for the orange segment, but low risk. So every orange analysis segment gets a score of 2. The green segment stretches across on either side of the power line. So we're going to consider the first 175 feet plus another 2,500 feet on the other side of the power line. So I got a total of 2,675 feet of contiguous pipe in the buffer exposed to the EMF, and therefore I'm going to get a look at my conversion table. Again, that comes into this bucket range here, this criteria here. So it's a medium risk, and every green analysis segment will be given a risk score of 3 for the co-location length risk factor. All right. So now I'm starting to see a pattern here, how we're applying our risk scores to our risk factors in there. Let's talk about the inflection angle, or what we call the bend in the pipe. For those of, if you think about it, you understand that if there's a change in the direction of the pipe or the change in the exposure of the pipe to the EMF on either side of the bend of the pipe, what you're doing is you're creating a voltage potential difference. And when there's a difference in voltage potential, current starts moving. And the likely place for that current to discharge is at those bends and those pipes out here. So we're looking, paying special attention to whenever there's a change in the direction of the pipe. So we look at our little red segment here. We see we have a 45-degree bend in the pipe right here, and then that previous analysis segment, there's no bend in the pipe. So to show the difference of how we would score the two analysis segments, you see this first analysis segment has zero degree change in pipe. So I look at my conversion table and I say the risk of that is very low. It's not no risk. There's still risk, but it's a very low risk. But I've got a change in direction in my pipe. I've got a 45-degree bend here, right? So I'm going to go look at my conversion table and I see if it's between 59 and 30 degrees, I've got a low riskiness. Therefore, I'm going to assign a value of 2 to my risk score for that particular analysis segment. And I'll repeat that for every bend in the pipe. And you can see once I get into the yard, it gets pretty busy. I got a 90-degree angle here. I've got 2 90-degree angles here, and I've got 4 90-degree angles right here. Right? So I'll go look at my pipeline, and again, go look at my little conversion chart. I see that when I have a change in direction of 80 degrees or higher, that's a high risk, and therefore those analysis segments are going to be given a risk score of 5 out there. So each of these analysis segments, you can bet, are probably going to be scored pretty high in our study. The gold segment, or the orange segment and the green segments, they have no change in direction. So again, each of the analysis segments in these pipeline segments would be considered low risk or very low risk, and each would be given a score of 1 for the risk factor of the inflection angle. All right. Let's talk about the crossing angle. This one was a little counterintuitive to me when I first got involved in this, putting the solution together. But what we're talking about is the actual crossing of the pipeline or the co-location angle, the angle of the pipeline within the co-location buffer, as it crosses relative to the power line. And the more perpendicular the pipeline is to the power line, counterintuitively, it is less risky. There's a less enhanced magnitude factor. You're aligning your pipeline with the electromagnetic field, and so there's less likelihood of the charge being induced on the pipeline out there. So let's take an example here. I see that I have no crossing with my pipeline for my red segment, so I'm down here at 0, 0, no risk there. Again, and no crossing for my blue segments. So again, I'm looking at my conversion chart. I got no risk, 0. So each analysis segment in the blue pipeline, the yard, would be given a score of 0 relative when it relates to the crossing angle. Same for the orange pipeline segments. There's no crossings, right? So, but I do have a crossing at in my green segment. Right there, I've got an 85-degree crossing right underneath the power line. And so if I go look at my little conversion chart here, I can see that it's a fairly acute angle relative to the pipeline. So it's the pipeline is pretty well lined up with the EMF, so it's a low risk right there. You know, when I first looked at this, I thought, well, geez, we're right next to the power line. Why wouldn't that little segment right there be a high exposure? But you got to consider the crossing angle and how it lines up with the EMF. So now that little 25-foot segment right there, in terms of crossing angle, is greater than 80 degrees. So we're going to consider it very low risk, and we're going to give that analysis segment a score of 1. So just as a hypothetical, let's assume that the pipeline coming out of the yard took a hard right and then crossed the power line at a 35-degree angle. In that case, I would give that analysis segment right there a crossing angle 29 to 60 degrees, right? Therefore, it's considered a medium risk, and that analysis segment would be given a risk score of 3 for the crossing angle. That's hypothetical, just trying to clarify, what it would look like if you had a flatter intersection with your power line and your pipeline out there. But for this example, again, we had an 85-degree crossing out there. All right, HVAC current. Again, as I mentioned earlier, if you can get the current on your power line from your power lines, that's the value that you want to use. And this table, this conversion table down here, is actually comes from the INGO report. They tell you if you've got these power line with this kind of voltage or amps current load on there, then this is how you would score your risks, your pipeline segments at risk. As I mentioned earlier, sometimes it can be very difficult to get the power company to release their current data to you. There are some third-party data sets available out there. If you guys want to contact me afterwards, I can tell you where to get that data. But they will tell you, they will give you the center line of the power lines, and they will also come with voltage. So if you can't get current, why not use voltage? Voltage is the design capacity of the line, so you can assume that if it's designed to carry 500 kV, then it's going to be designed to carry a pretty heavy load as well. So if you can use voltage, current, use it. If you can't, use voltage as a proxy. So in our little example here, I remember I said this was a 500 kV line. I'm going to assume that we've got over 1,000 amps running through that pipeline. So everything in this 2,500 foot co-location buffer, all of my analysis segments are going to be scored, are considered very high risk, and they're going to be given a score of 6. So you might be thinking, well, Andy, there's a lot of consistency or constants being used throughout this example, and yes, you're right. But think about it in the larger context of what we're trying to assess. This is a very small setup, kind of a subset of pipelines. But what if you had 7,000 miles of pipe, and you're looking at transmission lines, smaller voltage transmission lines, or smaller current, carrying less current through the pipeline or through the power line. So keep in mind that while this example is might seem kind of homogeneous, if you look at it from a much larger perspective, you're going to get a lot of variations in your risk scores here, based off of the proximity to the power lines and the load and the current that's being carried on those power lines. But in this example, we're all working in. We're going to assume that everything's the amps are over 1,000 kiloamps, and then everything's all the analysis segments are going to give a score of 6. Soil resistivity. Actually zoomed out a little bit on our perspective of our pump station and our scenario. The pin here down at the bottom is the actual location of our pump station. I asked our GIS team to generate this map and zoom out because I wanted to see if there was some actual variety of soil resistivity in the area. There is. You can see 588 ohm centimeters here, 9,999 ohm centimeters here, 1,000 ohm centimeters here. Just happens to be that in the area where our pump station is, it's the soil resistivity is all the same. So where did we get our soil resistivity? Did we go out and take soil resistance readings out in the field everywhere along our pipeline? We did not. There are some third-party data sets available out there. The USGS will provide a data set called the SERGO data set. And that SERGO data set comes with soil conductivity. And with a real simple little calculation, you can convert that conductivity into a soil resistivity reading. And we found that to be pretty accurate. We've been out in the field and we did our GIS analysis, did that conversion, went out in the field and did some testing, and we were pleasantly surprised that the data that we got from the USGS was pretty accurate, and the conversion, the calculation that we did was accurate as well. So our pump station is operating in a fairly homogeneous soil resistivity area. So if I look at that and I look at this, I can see that the actual calculation that we came up with was 600 ohm centimeters. So if I go over and look at my little conversion chart for soil resistivity, and again, the lower the resistivity, the less the resistance to soil, the higher the risk. So I've got 600 ohm centimeters. That's pretty low resistance. Our conversion table tells us if we're less than 2,500 ohm centimeters, we're at high risk. Therefore, every analysis segment in this example is going to be given a risk score of 5. Okay. Okay. All right. Now let's talk about inductive coupling risk factor for pipe design, and in particular the coating resistance. As I mentioned earlier, if you have a high resistivity on your pipeline due to your coating, then you're keeping that charge on the pipe, and that charge is looking for somewhere to discharge and get off of the pipe and into the ground. So what I'm going to take three variables, what we call a composite risk factor, and I'm going to take three variables that typically your integrity management team will know, and combine that into one coating resistance factor. So I'm going to consider coating type, and again you can see that I have FBE, high resistivity on the pipe. Therefore, if my pipe segment the analysis segment happens to have FBE on it, it's going to be given a score of 5. As I get older technologies and down through the chart here, you can see the risk of the resistance of that particular coating type goes down. So I got lower risk. Same thing for coating age. Newer coating, we're getting really, really good at putting coatings on our pipe. Fewer holidays on our pipe. So the newer the coating, the less likelihood there is to have holidays, the disbondment, cracking, and less opportunity for the charge to dissipate. But the older you get, obviously you're going to nick, it's going to disbond, and there's going to be more holidays. And so the older the coating, the more likelihood, the less risk there is, because there's opportunity for the charge to dissipate. So you're going to get a lower score. Newer pipe, higher risk. Older pipe, lower risk. Right? And then coating condition. When you're out in the field, and a lot of your integrity management groups will tell their inspectors when they got the ditch open and they're doing their bell hole inspections, give us an assessment of the coating condition out there. It tends to be in your integrity management database, it tends to be something like good, fair, and poor. So it's a very subjective assessment by the inspectors out there. But it's still something you'd want to kind of incorporate into your composite risk score here. So this is an example of what an inspector might come back and say, yeah, my coating is in good condition. So it's in good condition, therefore it's going to keep the charge on the pipe, less opportunity for dissipation. So I'm going to give that a score of risk score of 5 for that particular risk factor. I say it's a composite risk score, so I'm trying to take all three of these variables and combine them into one variable, so that it kind of simplifies our equations or simplifies our analysis. But I might think that my coating type, I might rely on that a little bit more than I say the subjective assessment of my inspector out in the field. There's some very clear documentation out there about coating types and how you should consider those and how you consider the risk of those coating types. So I'm going to rely on coating type a little more than coating age and coating condition. So we can do this by weighting the values of those variables. So type times 1.6, age times 1.3, and condition times 1.5 or 1.1, sorry. And bring all that together to get a coating resistance for a particular analysis segment. So let's take an example here. Let's go back to our example, coating resistance. I have my a red line coming in. It's FBE coated in 2007. It's in fair condition, so it came up with a composite score of 19. If I look at my risk table here, conversion table, 19 to 15, it's a medium-high score, and therefore it's going to be that analysis segment, all the analysis segments in this particular the pipeline segment will be given a risk score of 4. Now there is a concept of dynamic segmentation. Let's say my coating changed from here to here, then I would create another pipeline segment. But for this example, which is our pipeline segment, and all the analysis segments applies to this particular stretch of pipe right here. Going on further down into further example, let's say I had my facility piping was DW tape installed in 2010. It's in fair condition, so based off of our composite variable, we got a score of 16. Again, I'm going and looking at my conversion table. A score of 19 to 15 means a medium high. Therefore, all the analysis segments in the facility piping will be given a score of 4. Similarly, coal tar, older piece of stretch of pipe out here, installed in 1972. It's in poor condition. It's coal tar. It's old technology, lots of holidays, lots of opportunity for that energy to get off of the pipe. Therefore, my composite risk score comes up with a score of 3, less than, based off of our conversion table, less than 3 means very low. So all the analysis segments in my green stretch of pipe, green segment, will be giving a score of 1. And then pipe design, pipe diameter. If you read the documentation, you'll see some documents talk about smaller diameter pipes, or the diameter of the pipe should be considered in your assessment. However, they're almost like footnotes in the documentation. There doesn't seem to be any really. As you're reading the documentation, you get the sense it's there conceptually, it makes sense, but we don't have a whole lot of proof. But if you have your pipe design and your pipe diameter data and you want to incorporate that into your study, generally it is the smaller the diameter of the pipe, the higher the risk, and that's due to the enhanced magnitude of the EMF onto a smaller surface area exposed to the pipe. Larger diameter pipes then would be considered less risky. You got larger surface area, larger opportunity to spread that charge around on that larger surface area out there. So larger diameter pipes, less risk. Smaller diameter pipes, higher risk. And again, read the documentation if you want. It's almost an afterthought or a footnote to considering pipe diameter as part of your threat assessment, but it's mentioned, and you can certainly incorporate it into your threat assessment if you want. So if I were to look at my ongoing scenario here, I've got a 24-inch line coming into my pump station. So 18 to 24 inches is considered a medium-high risk. So all the analysis segments along the orange segment here will be considered given a risk score of 4 for their risk factor. 20-inch main line and coming into the yard, 20-inch again back out on the main line of the green segments. Same thing, 18 to 24 inches. Medium high risk, give it a risk score of 4. Okay. So now I've gone through all of my risk factors. I looked at their current values. I looked at their current state, and I assessed them for their riskiness by giving them a risk score. The higher the risk score, the higher the potential for risk. I know a lot of you are probably asking, okay, how come you go 0 to 5 sometimes? Sometimes you go 0 to 6. Sometimes you go to 0 to 1 to 5. Wherever possible, we pulled documentation. We relied on existing documentation where they gave us the criteria. We tried to leverage that criteria. So we found that, different criteria and different documentation gave us different standards. If we couldn't find documentation, but it was mentioned as part of the as a risk factor, then we applied some just evenly spread out the buckets over a 1 to 5 range out there. So you do get a different range of risk scores for each risk factor, but that's not really important because we're just trying to compare risk for those particular analysis segment for that risk factor. We're not comparing them across different risk factors. So what I'm going to do next then is I'm going to bring it all together here. And I'm going to bring it all together into what we call a relative threat score. And essentially what I'm going to do is take all of those risk factors that we assessed and sum them up for each analysis segment. So each analysis segment, we're going to, and again, I just showed it here from the red to the blue. But so all the risk scores for those risk factors are summed up for that particular analysis segment, giving me a score for that little 25-foot stretch of pipe for how risky that particular pipe is. That particular analysis segment is. Well, that's good, but you're going to go out and look at just 25 feet of pipe. What we're going to do next is, we're going to take the average of the all of the risk scores for those analysis segments and average that across the pipeline. So if I take my risk factor risk scores for all the analysis segments in the red segment, I get a 26.34 risk score for that analysis segment. Same thing for the blue segment in the yard. I get a 26.91. That's my average risk score of my analysis segment. 24.39 for my orange segments, and 26.58 for my green out there. So now I understand at a high level what segments of pipe are at the highest risk, and if I wanted to drill down into those particular segments, I could get down to the 25-foot analysis segment to see what particularly is driving that risk score for that particular analysis segment. So not surprisingly, the blue segment with all of the changes in directions and the bends in the pipe came out as the highest risk segment of pipe at highest risk. So what I'm going to do then is I'm going to dispatch the outside dogs. I'm going to pick up the phone. I'm going to call Jordan, my field crew, and I'm going to say, hey, you guys need to go out and do a field assessment at the yard there. Take a look around. Take your portable reading devices. Get me some AC current density readings out there and see what's going on and see if we need to mitigate them. Okay. So now I've got my crew. I got the outside dogs. I got them in the right location to go out and see if there's a threat on the pipeline. And Jordan and his outside crew are very thankful because they don't have to be walking the entire right of way, taking AC current density readings. They know exactly where to go in the 100-degree heat in Texas out there. The risk factors that I showed you earlier, which is a subset of many different data sets that if you have that available, and your integrity team probably does have this data. If you want to incorporate these data sets into your threat assessment, I'd highly recommend that you do it. If you have your inline inspection results, you got your pipe tally for your ILI runs, run that, lay that into your co-location buffers there. And if you've got a bunch of anomalies being called out, external wall losses called out in close proximity to a power line, if I were a betting man, I would say it's probably AC current, induced AC corrosion going on there. Induced coupling and accelerated corrosion, I apologize. Your cathodic protection system, how effective is it? If you can get that data, how you may still have a corrosion going on your pipeline, but if you got a CP system on there that's effectively mitigating it, then you'd want to consider that as well. Close interval surveys, you're out there detecting holidays on your pipe and the coating. Again, if you have holidays and you got a few holidays in a very close location to your pipeline, might be thinking about induced coupling and inductive coupling and accelerated corrosion. You did hear me talk a little bit earlier that if you have, the single most important reading indicator that you do have AC induced corrosion is AC current density readings. If you have those test stations out there and you have that information available, then by all means put that into your threat assessment as well. This example that we walked through here was assuming that you were starting from scratch and you didn't have a monitoring program, you didn't have any test stations, and you were collecting this data for AC current density. But if you have it, by all means bring it into the equation, the modeling up there. Okay. So there's, again, AC current density. If you're like me, here's an example of a coupon that you'd put out next to your pipe. It's a Triton coupon. We sell this. But if you're like me, I'm an inside dog. I'm going to put an RM4210. I'm going to put a remote monitoring unit on top of it so that I don't have to go out into the field, and from the comfort of my desk, I can actually get some real-time readings of the AC current density that's being on my pipe. INGO will tell you that if you have AC current density of 100 amps per meter squared or more, you definitely have a problem. You might have a problem if it's between 20 and 100. You've got no problem, or you're doing okay if you got less than 20 amps per meter squared. INGA came out with another set of criteria. It's not listed here, but in the INGA document, that SP document that I talked to you earlier, there's a correlation between the DC current and the AC current on the field. So if you're collecting both DC current and AC current with your coupons, you can come up with a criteria to see whether you have a problem or not as well. So hopefully with the framework and the risk factors, and show you how to apply those risk factors, I've given you a foundation for implementing a solid AC interference continuous assessment program. A program is a set of projects that you do over and over again that are benefit by managing them together. So think of your CP system, your CP close interval surveys as a program, your ILI as a program. now you got AC continuous assessment program. And when the auditors, the PHMSA come knocking on your door and they say, show me what you're doing for AC interference, you can show them that, hey, I've got a pretty well-defined, defensible, logical approach to monitoring AC interference. So with that, I'm going to wrap it up, see if there's any questions here. And let me open up my dialogue here, read through my questions. There is one question here, but I can't, how do I? So how do you convert the data from the USGS to get the soil resistivity? Very good question. It's a real simple algorithm. I will reply to that in an email. I don't have that. It's a simple equation. I don't have that equation with me right now, but it's real simple. Again, the USGS Sergo data set gives you conductivity. You apply a little conversion formula and you get the soil resistivity out of it. So Kirby, thank you for your question. We'll get that to you in an email response. Sorry, apologize, I don't have that equation with me on hand right now. Are there any other questions here? Let me see. There is, but I'm having a hard time. Let's see here. Here we go. Unless the pipes are isolated at, sorry, I can't see that, at joints, I guess it is, at each spot, why would you not consider the pipe as a contiguous link? Unless the pipes are isolated at each spot, why would you not consider the pipes isolated continuously? That's a good question. We go back and we'll research that one as well. Haven't really thought about the isolation along the pipeline. Again, we were coming at this with this initial threat assessment with the data that we were available at the time to, and all we had was the pipe center line. We also had the power transmission center lines. We didn't have any isolation points along the pipeline, but certainly if you have that information, then you can consider that as part of the contiguous segment. Your GIS team could incorporate that easily enough. So how are we doing on time, Anna?
It is 11:09.
11:09. So we're past our hour here. There are a lot of questions here. I'm not sure I'm going to. I'm not going to have time to answer all these questions. So we will take these questions offline, get you a response, and follow up with you, and hopefully answer all of your questions out there. Apologize. Nobody ever accused me of being too verbose here or too shy. I get on a roll and lose track of time. So let's go wrap it up real quick with one last slide here. You've gone through 3 sessions so far. What is AC interference? We've given you some mitigation options, talked about how to prime your program with AC threat assessment. 2 weeks from now, part 4 or final part in our series, it will be on monitoring. What is it you actually need to do, and where do you need to go to put these monitors, and what are you looking at when you get that data out there? For those of you who have attended all 4 of our sessions, who do attend all 4 of our sessions, we'll be sending you a ball cap, either a BASS cap or a AI cap. Clay Brailsford and I have a little competition going about who's going to request what cap. So if you guys, and there's a steak dinner involved here, so if you guys don't mind, in Clay's absent here, I'm gonna put a plug in for an AI cap. So you guys if you attend the 4th session, send us an email and all 4 sessions, and we'll send you a ball cap. Just joking. If you want a BASS cap or AI cap, doesn't matter. We'll send you one. Everyone, thank you for your time. I did run over lots of material. We did this at a high level. There's a lot more to cover in AC threat assessments, but I appreciate your time. Hope you found this informative, and look forward to seeing you in about 2 weeks. So thank you, everyone.